many of DSO's problems throughout our portfolio have to do with complexity in one fashion or another. But there's probably no more complex domain than those relating to social dynamics, understanding and predicting how humans will behave. So some of the areas we touch on in this area are models of social dynamics, causality in social systems, and human-machine interactions. And we're also interested in wargaming and conflict simulation, and also in understanding social media tools. So the third area that we talk about is anticipating surprise. But of course, what I mean by that really is anticipating scientific surprise. And I want you to think about this particular focus area as being about one thing, and one thing specifically, and that is speed, right? So increasingly, the problem that we face as a nation is how can we capture and exploit knowledge more quickly than our adversaries can? And that really drives what we do in this particular area. It really is, in terms of topics, is a rich area. A lot of the work we do here is in materials, functional materials, structural materials, looking at energetic materials, and also manufacturing processes. But another area in this category that's also very large, and we'll be hearing about it in just a few minutes in the large auditorium, relates to weapons of mass destruction, WMD and WMT. And I think you'll also be hearing about this particular area given the panel that we have today in just a few minutes. And then last, and certainly not least, is on the left, what we call frontiers in math, computation, and design. And as you can see from the diagram, we think of this as being cross-cutting. And sometimes it's difficult to tell where the math begins and where some of the other areas start. But some of the areas specifically within math that we care about include planning and optimization problems, because these are very key to a number of military problems, commercial problems too, but military problems like logistics. One area that has particular attention we've heard a great deal about, and we'll be hearing even more about this morning, is in machine learning. And like the other areas, our interests in machine learning tend to be focused really on the fundamentals. What can't we do in machine learning, and how can we develop new ways of doing machine learning that will go beyond those limitations? We're also interested in advanced design tools and alternate computing models. So as you can see, that's really a lot of real estate. So now let me say a word or two about the people who let us cover such a wide amount of real estate. So these are our program managers. And as you can see, it's a diverse group with if you can read the fine print, a diverse set of interests. And I think all of them are, or at least should be, in the room today. I invite you to engage with them after this meeting, directly after the meeting, or any time during the rest of the meeting. And I also invite you to contact them through the webpage and talk to them about your ideas and your interests. So now, let me say a few words. I wanted to say a few words to give you some motivation about some of the kinds of programs that we sponsor in DSO. Before I do that, though, I wanted to say one last thing about a topic that we call disruptioneering. So I said a few minutes ago that speed is critically important, and this quote, deliver performance at the speed of relevance from the National Defense Strategy, is exactly what I'm talking about. Disruptioneering is a mechanism that we've instituted, we've pioneered in our office that directly speaks to that goal. It is a new way of doing business, and the concept here is to do very high-risk concept exploration in a short period of time. And by short, what I mean is that we have demonstrated that we can go from a solicitation to a complete program, including all the contract negotiations, in under 90 days. We've now done this 5 times, and we're starting to get good at it. And we anticipate that there will be many more of these disruptioneering opportunities in the future. Okay, so finally, let me, again, just to motivate our discussion and to educate anyone who's not familiar already with DSO, I want to say a couple words about a few programs that we've had recently. As you can see from this slide, this is sort of a list of the recent projects, the recent program announcements that we've had. They're distributed across all 4 of our focus areas. So let me just say a word about one of the more important ones, Sigma Plus. This is something that you'll be hearing more about in just a few minutes. But Sigma Plus leverages a previous program called Sigma, which demonstrated a scalable distributed sensing of nuclear threats at the city scale. And Sigma Plus expands upon that and adds radiological to the radiological and nuclear, chemical and biological threat detection. SCORE is a program that is in the complex social systems area, and it grew out of a really compelling need in that domain to understand reliability and replicability in studies. There is a tremendous variation and a lack of reproducibility and replicability today. So think of the goal here as being able to present a DoD user interested in social science studies and the results from them with something like a confidence score, not unlike a credit score, to give them an informed idea of how to estimate the value of the results. And I think finally is a program called Space Environment Exploitation, SEA. And this is about understanding and modeling near space. So this picture shows a beautiful picture of the Aurora Borealis. It's awesome, it's beautiful, it's extremely large if you think about it. It's also completely unpredictable. So what we want to understand and be able to predict are events in space coming from natural effects and man-made events, which leads to a huge problem in multi-scale physics because physics is happening on extremely small to extremely large distance scales in modeling and in sensing over such an enormous area, enormous volume. Okay, a couple more comments. These are actually not specific to DSO only, but they are a couple things that DSO facilitates for all of DARPA. Recently, there was an announcement called AIE, Artificial Intelligence Exploration. This is very much, this is a DARPA-wide initiative in artificial intelligence. In form, it is very much modeled on the disruptioneering approach that I described a few minutes ago. And so I invite you to look at that webpage if you haven't already. And then finally, there is a program that DSO runs for all of DARPA called the Young Faculty Award. This is, for us and for the agency, a tremendously important program. It's really, again, about speed of innovation, trying to learn from a much larger community than we traditionally have been involved in. It's awards that go to junior research, both university and not-for-profit, for 2 years, but expandable up to 3 years, up to $500,000 in total. And it helps us attract a new generation of performers and collect their ideas. Okay, so with that, we can get to the good part. Our goal for the rest of the session is going to be to talk about specific ideas and specific areas DSO may be interested. And there is, as always, no better people to talk about ideas at DARPA than the program managers. So let me introduce the panel. And each of the panel members are going to talk for a few minutes and give some ideas about their interests. After all 3 of them have gone in turn, we'll open the floor up. I think everyone by now knows the drill. If you want to ask questions, please submit them through the D60 app. And by the way, and I think you know this too, submit them at any time. You don't have to wait to the end. In fact, it's better if you type in your questions as you think of them. So, okay, so our 3 representatives today from the office. Let me begin with Dr. Bill Carter. He is, I would like to say, he is the most recently minted DSO PM. He's been around for a month and a half, but that's not true anymore. So our turnover at DARPA, we have many program managers coming in all the time. So he's no longer the newest PM, but he's the second newest PM. Before this, he was the director of Sensors and Materials Lab at HRL Labs in Malibu, California. He's a materials scientist. He's strongly associated with the dandelion picture, and if you don't know what that is, please ask him. Bill will explain what the dandelion picture is. But he's worked across a wide range of aerospace and automotive domains. And the little known fact that I'll tell you about Bill is that he's an avid traveler, and he's hitchhiked the Himalayan Trail, which is not easy to do. So please ask him about that if you have a chance. Our second speaker is going to be Dr. Michael Fitty. He's a veteran, comparatively. He's been around DSO since September of 2016. He has a very large portfolio of programs that he's responsible for. His research interests are in electromagnetic inverse problems applied to imaging and in engineered materials design. So Mike, what I'll share with you about him is anyone who's been around Mike appreciates that he's a beer lover. And you know, I'm really not supposed to say this, but I've been told that he's secretly working on a program to make a quality IPA without any hops. So you could talk to him about that. And our last speaker is Dr. Ann Fisher. She is a chemist. She joined DSO in January of 2017. She also has a very healthy portfolio of programs within the office, and they address a number of topics, probably too many to mention, but I'll mention a few of them. Chemical synthesis, developing wide area highly sensitive and network chemical detection technologies, and molecule-based data storage and computing. Some of our interests include exploiting tools, techniques, and approaches known in other areas, things like artificial intelligence, to accelerate and improve the way we do and think about and approach chemistry. And the fact I'll share with you about her is she actually enjoys being called by her new nickname, which is the Chemquistador. I'm not sure why. So anyway, it's a great group, and with that, Bill.
Thanks so much, Mark. Okay, thanks everybody for getting up early to come see us. I really appreciate it because I'm new here. So as Mark mentioned, until recently, I was the Director of Sensors and Materials at HRL out in Malibu, California. So I want to actually save you some work typing in a question on the app. You know, why would you go from Malibu to Arlington? What the heck are you doing? I mean, you know, it's obviously a beautiful place out there, but quite frankly, DARPA is a very, very special place. I want to change the world, and this is a place to do it. And as a material scientist, I can't think of a better place to come to change the world than the birthplace of material science, you know, 50 plus years ago. So this is a really unprecedented opportunity. I think the other part of that answer is that I feel a really strong sense of urgency, especially today in today's environment, in terms of getting materials, high-performance materials, out of the lab and onto platforms. And this is a really non-trivial activity. It's something we've been struggling with as a species for a very, very long time. If you look at the top level, say I'm a platform designer, I look at materials as both an enabler and a huge source of risk. And one of the pieces that is, I guess, a hallmark of how the US prepares itself and then prosecutes war is to combine cutting-edge science with industrial might. You know, being able to ramp up and produce a lot of something on very short order. And so the reason I touch on that is my perspective with respect to material science is that we not only have to think about performance, but we also have to think about all the other pieces that are really important when you're a platform person, when you're thinking about a mission, you're thinking from a mission perspective, what do you need to do? You need to think about scale. You need to think about manufacturing. You need to think about the risks that these materials, even though they're very attractive from a performance perspective, how do those risks play into the development, deployment, and use, longevity of platforms? Okay, so the area that I'm looking at right now, we're calling materials for extreme environments. And I think if you were here for the last couple of days, I don't have to convince you that many of the key platforms that DARPA and actually the military is looking at in terms of, creating a competitive advantage for the US, they exist. They live in very, very challenging environments. And I'll mention a few and then focus in on one in particular. So the first I want to talk about is materials for hypersonics. This is an extremely challenging environment. There's also underwater and space, and they each have their own challenges. They each have opportunities as well from a materials perspective that I think we can look at and start to harness. Okay, so let's start with materials for hypersonics. As you may have seen in some of the talks, this is an absolutely incredible environment. Incredible platforms are being proposed, and we wish to develop and field these platforms. And in that environment, you have amazing energy and challenges for the materials. The opportunity is that we have, for instance, at the very front of the aircraft, we have a very high temperature. We have a lot of ionized gas. We have gases that are not in equilibrium with themselves, even molecules and disassociated species that have, we can't even define a temperature for them because they're not in equilibrium. But you have all of that activity at the front of the vehicle, and that starts to do amazing and horrible things to the materials. So they will erode, they will fail in various spectacular ways. And that's where the risk comes in for the platform folks who are trying to design and field these platforms. Okay, so what can we do to help them? If you look at what they're doing today, they're utilizing materials that are actually pretty old. These materials have been around for 40, 50 years. And they tend to look at them not as we look at them from a material science perspective. We look at, oh gosh, we could get the highest temperature capability possible or the highest strength possible. They look at them from the perspective of the minimum properties that they will be able to achieve. So if I think about strength, I really don't care about my world record strength if I'm a platform designer. I care about what is the minimum strength that material can give me, and that's what I design to. And so our job is to really try to push that as high as we can and really understand what are the stochastic aspects of materials and what are the distribution of properties that we get out of those materials, and try and really fit them into the application. Okay, so if I want to encourage you to come talk to me about materials in these incredible environments and how we can push them into platforms, there's really three kind of topic areas. These are sort of big buckets that I'm looking at right now. One is to look at current materials as systems and ask from a scientific perspective, what can we do to understand those materials better, to buy down some of those risks that the platform guys see? And if I develop a program in this area, those platform folks are going to be right there at the table trying to answer that fourth Heilmeier question. You all have them memorized, right? You know what number 4 is, I'm sure. What difference will it make if we're successful? And in my mind, that's actually practically the most important question. We want to be able to tell them, okay, here's the risk, and then if you use this material, here's how much better the platform and the mission can be. Okay, so what science can we do? I'll give you just a concrete example, but this is obviously not a limiting example. But carbon-carbon composites, these are the highest temperature capable materials that we have today. And even still, in a hypersonic example, they don't last very long. And so we tend to think about coatings. And the interaction of a lot of these high-performance coatings with that material, it's non-trivial because carbon-carbon is a porous material. It has a lot of stochastic behavior, and the manufacturing base is, quite frankly, still pretty immature. They are doing the best they can with these materials to develop these platforms, but it's really a non-trivial endeavor. Okay, so understanding those interactions, how those materials can live over time. The next area is thinking out beyond those current material systems. Not just what can science do for those material systems to get them onto platforms, but let's think about how we can then harness that energy gradient that I talked about in that particular example, of hypersonics, to reinforce those materials. And if I go and I take some inspiration, say, from nature, one of the things that we can do is harness that energy gradient to move mass. The simplest example of that would be a heat pipe that pulls heat away from the leading edge back to a heat sink somewhere else on the vehicle and enables, a lower temperature and longer flight times. But that is not a limiting example. There are a lot of different types of energy gradients you could think about harnessing at the front of the vehicle. It could even be, the ionized gas on the outside. Maybe we want to harness that. There's also the chance of looking at things like electrolytes. Some materials become great ion conductors at these temperatures, and you could imagine being able to replace material at the surface of the vehicle so you maintain that aero surface. Okay, so those are kind of future enablers. And then the last thing that I've identified and I think is an important topic is the physics of testing. And there's really two things in testing. There's can I turn the crank quickly? Can I get my material into an environment in the lab that is representative of the environment that it's going to live in, and then turn the crank, with experimental cycles to be able to make that material better, more robust, and to buy down that risk again from a platform perspective. Qualification is another really hard problem. You all are probably aware, I have some background with my Boeing colleagues, but it took a lot of effort. It was a really heavy lift to get the very basic concept, very, very basic composite that exists on the 787 and other aircraft onto those airplanes. A good decade and a lot of money. And so how can we buy down the time associated with qualification? And so I think getting a bunch of really creative, smart physicists, and engineers and platform folks in a room to talk about that is something that I have ambition to do, and see if we can find some loopholes in physics that can allow us to create some really unique, interesting testing capability. If you look at the scaling associated with wind tunnels, if you want to go from Mach 5 to Mach 15 to Mach 25, physics is not your friend. This is really hard. So let's get our thinking caps on and see if we can crack that nut. Okay, so up until recently, I was on the other side of this equation, so I have a good sense of how all of you are looking at me now. But please come talk to me. I'm really excited to be here. I have, like I say, a very strong sense of urgency that we need to learn how to turn those development loops more quickly and fewer times in order to get materials into these very important national platforms and assets. So thanks very much. So with that, I will pass on to Mike Fitty.
Thanks, Bill. And thank you all for being here. I'm looking for those loopholes that Bill mentioned. And I wanted to give you a big picture of the kind of problems that I think we should be looking at, and then from that context drill down to three example problems that I think are popping up right now, but they're just three of many. So my interest is in electromagnetic waves and their interaction with matter from DC to daylight. If you think about the space of all the things we could know in that domain, then I think you all know the story about, if what we know in this space is confined in here, then the more we know, the bigger that boundary. So the more we know, we don't know. And I'm very interested in exploring that boundary and trying to find the loopholes, to find the opportunities, perhaps, for light-matter interactions that we've missed, or we've perhaps just ignored because of the way we think about light-matter interactions or electromagnetic wave-matter interactions. So I have more of an optics background. So I was brought up thinking in terms of, there's a certain space in which ray optics does a really good job in describing propagation of light through certain structures like lenses. As you can engineer smaller structures, you need a wave picture. At some point, you need an electromagnetic wave picture. At some point, you need a quantum picture. What's beyond that? I fail to believe that we've really got all the modeling sorted out yet, and that these are sufficient to describe what we are dealing with today and what might be coming along to surprise us in the future. And of course, this has many applications. We're interested, from a mission perspective, in detectors, in imaging, in sensors, in switching, in harvesting energy. These are all applications that are grounded in the models we have in our heads for how to describe electromagnetic wave matter interactions. And I would argue that in the last 15 years, there's been a number of mini revolutions in understanding or in increasing our awareness of what interactions might be available to us. We're just beginning to understand. I mean, going back to my ray optics analogy, I think we all felt that we learned at our mother's knee that Snell's law was probably true, that it was settled law, so to speak, and it isn't. Okay, I mean, we now know that it needs to be generalized to include the boundary. And if we start putting sub-wavelength structures on the boundary, we have to rethink how we implement Snell's law. And that's a real opportunity when it comes to designing optical structures. We are now able to fabricate structures smaller than the wavelength at which we might wish to operate. And therein lies a huge, I think, breakthrough in capabilities. I guess the first evidence that this might be possible is if you go back to the late 60s, early 70s, when the superlattice was developed. And just a few layers, the geometry of just a few layers of material, give you enormous functionality. Well, in optics and electromagnetics, we tend to deal with the materials that nature gives us. And those materials are made of atoms, and we characterize their electromagnetic responses in terms of constitutive parameters, averaged parameters, permittivities, permeabilities. But we can structure materials now. And so instead of approximate properties based on a random phase approximation at the atomic level, we can structure materials so that coherent effects, phase effects, like in the superlattice, can start to affect the bulk properties of materials made in that way. So some of the ongoing programs we have are looking at that very question. What kind of structures on the sub-wavelength scale can give us new functionality? And one example I'd throw out, which is very exciting, is we can engineer materials now which may be somewhat lossy, but perhaps not fundamentally lossy, that have an index, a refractive index of 0. If you think about that for a minute, it can be impedance matched too. So not necessarily difficult to get electromagnetic waves into it. But other models we have in our heads right now suggest that those materials could conceivably have much larger nonlinear responses, which could be important in many applications, parametric amplification, switching. But it's a mix of models, and the experiments suggest there's something to that. But we really need a more holistic approach to some of these areas to get our arms around better models that are in step with the kind of fabrication capabilities that we have today. Fully quantum models are really hard. We have a program looking to try and understand what the fundamental limits of photon detection are. And if you take an abstract theoretical perspective of that, you can at a very high level say, yeah, you should be able to make a detector that has 0 dark counts, should have perfect efficiency and accurate photon number counting. But we don't know how to map that math into a physical platform that allows us to make those kinds of detectors with those properties. The other interesting thing, I think, if you go to low frequencies, which of familiar use to people in the seismic industry or looking underwater, I think we're just beginning to understand that our thoughts about imaging, for example, where I think everyone in the room would probably say, well, if I want really high resolution imaging, then I need bigger and bigger lenses. The Abbe limit, Rayleigh's criterion. It's not true. I mean, we know enough now from the recent advances in computational imaging that with very sparse data and a certain amount of prior knowledge, you can get high resolution imaging. But we also have always kind of felt that if we could get closer to the object we're trying to image, we could probably get higher resolution if we're in quite the near field. So why don't we just use longer wavelengths? It's counterintuitive because you'd think, well, I can't really have a lens that's 30 kilometers in diameter, but I'm in the near field. I have to think differently. My way of forming an image or calculating an image, computing an image from near field data with very low frequencies completely changes the paradigm of what I'm able to do. And it's an interesting space to explore. So I wanted to kind of wrap up with 3 examples that are on my mind right now, and I'd love to hear of other sort of game-changing, potentially disruptive examples that you might have in this electromagnetic matter space. But these 3, I think, are particularly interesting right now to me. One is that I mentioned quantum and the difficulty of really analyzing in a quantum way more complex structures. But recently, it's kind of clear that we've stovepiped quantum optics or quantum electrodynamics in a way that might have forced an unnecessary separation between that and more classical optics. We think in terms of qubits and their fragility and decoherence problems, and we're rushing to try and develop quantum computers. It's hard to do because we're thinking about the problem in the context of that model. But really, one of the important attributes of a quantum system that's often cited as the way of distinguishing a quantum problem from a classical problem is a phenomenon like entanglement. And recently, many groups have found that the equivalent of entanglement is clearly present in classical optical experiments. Once you start looking at more complex degrees of coherence or correlation in classical optical experiments, then you can entangle quantities like amplitude and polarization or spin with large numbers of photons. So is there an interesting space here to explore in terms of revisiting some classical optical systems, but thinking of them in terms of the quantum model that has been driving a lot of the effort in terms of developing quantum cryptography and quantum computing. A second example goes back to structures and engineered structures. Of course, we'll probably never be able to fabricate structures with the precision we really need in order to have this exquisite phase coherence that I'm talking about, that we can benefit from. On the other hand, we're always going to want to do things with somewhat broadband radiation. And can we live with some degree of disorder? And what's really interesting, and recent research points to this, is that some degrees of disorder don't mess up that phase coherence. and other kinds of disorder, destroy it immediately? Can we get a better handle on the kinds of disorder that can be our friend even, rather than destroy the kinds of phenomena that we're looking for? And this branches into biology, which I could elaborate on a bit. It branches into harvesting energy. It branches into the consequences of structured materials and managing quantum vacuum fluctuations and vacuum energy densities, which can have some interesting chemical consequences. And then the third one I wanted to talk about, I'll briefly bring up, is going back to low frequencies. We're surrounded by background electromagnetic waves, everything from Navy communication towers at 30 kilohertz, lightning, power lines, machines, everything around us. We have all these sources of opportunity which could open up the door for us to exploit for imaging and sensing. Very low frequencies will penetrate most materials, and low frequencies give the opportunity to take my imaging resolution example from earlier to, for example, see inside containers if we have the right sensors. We may need quantum sensors. So going full circle, looking at these very low frequencies, we might need Aharonov-Bohm sensors in order to detect subtle changes in background potentials arising from the presence of materials in these structures. Opens up a whole world of new possible imaging capabilities. And the flip side to that of DoD relevance is, what does it mean that you can shield anything any longer? We don't know what that means anymore. So these were just 3 examples of many, and I'd really love to hear your ideas at this sort of boundary I was describing of what we know and what we don't know, because none of us want any Sputnik-like surprises coming from this domain of electromagnetic matter interactions. So thanks for your patience listening to me, and I'll pass it over to Anne.
Thanks, Mike.
Yeah.
Good morning, everyone. So we sort of have been going on a journey this morning of scale. Started off at the materials level, down to the electromagnetic wave and various applications there. And I'm going to bring us up to, I think, the best scale, which is the molecular. So before 99% of you turn off your ears, I want to talk about 2 things, 2 reasons that you should continue to pay attention. One is that molecules are the building blocks of everything. Every biological system, every physical system. And the second is that there are tools out there in the world, in disciplines other than chemistry, that we need to harness and bring in to help us design and develop new molecules, new molecular systems, and new materials for DoD applications. So right now, the way we develop molecules for for an application, be it a medicine, an energetic, a polymeric coating, a dye, is an iterative, intuition, expert-driven, slow process. How do we understand in the vast space of possibilities for pharmacologically relevant molecules? This is molecules that could potentially be a small molecule medicine. The potential structure space is 10 to the 60th. That's incredible. How do we even think about exploring that space? What unexplored areas will provide interesting new and novel properties that we might be able to use for a variety of applications? And when I talk about properties, I'm talking about really fundamental things. I'm talking about things like solubility, permeability, electrical properties, some optical properties. If I take one molecule, it has many of these properties. If I have another molecule, it has may be the same properties, but they're different? How do we think about the optimization of properties for a specific application? Solubility matters in the medicinal field, and it matters in the field of energetics. So how can we think about understanding what the properties of a molecule are and how we might predict what molecules we need to develop for those applications by being able to look at those fundamental properties that are cross-cutting across all of the application spaces? Given the possible structure space, property space is probably smaller, but it's probably still huge, particularly if you think about the intersection and the interaction optimization of multiple properties. So where do we turn if we need to be faster, if we need to have better performance? We turn to computation, we turn to what you've been hearing about in AI, bringing in machine learning tools. But the way that chemists represent structures and the way that chemistry has been done for hundreds of years is based on molecular graphs. And if we take these graphs, which are structures, and we try to map them to properties, sometimes it works, and sometimes it doesn't. And we actually don't understand what features are important of molecules beyond structure, beyond electron clouds, beyond the quantum mechanics. How does that all play into the ultimate properties of a molecule? So if I try to take the way chemistry has been done and the way that a chemist would represent a molecule, you can think about those hieroglyphics that you see when chemists draw reaction schemes. And I try to feed that to a computer to do statistical learning, which is pattern recognition. What I get out in the end is a tool that can look at structural patterns that don't map to properties. Because we're treating these things, if we take hundreds or even thousands of descriptors or features that are structure-based, what we end up doing is learning structural patterns that sometimes map to these properties that we care about and sometimes don't. And we don't understand why and how and what the boundaries are for those mappings. Another challenge is that chemistry is inherently dynamic. And the way that we're thinking about this right now in mapping the chemical space to the machine learning space is static. We take static data, static representations, because it's what we have. We do have models. We have molecular dynamics models. Could we use those as features to think about the properties? For example, in a medicine, if I have a protein and I want a small molecule medicine to bind into that protein pocket, it's not a singular event. These two things are moving in solution. We need to understand, because those are the forces of that interaction over some time are what's important and what makes one small molecule medicine so much better than another, even when their structures look incredibly similar. It affects the fact that we have two molecules that might look to you exactly alike, but in three-dimensional space, they have one variation. One is toxic, and one is a therapeutic. How do we understand that in the vast structure space that we need to be able to look through to find new materials, new medicines, new energetics, new fuels, for all of the applications that we need? So I'm really interested in thinking about how we take the years of existing data that we have. We have a lot of data out there. Let's not recreate it. How do we take that data and the context of that data? We don't just want tables, molecular graphs, so graphs showing some feature in a static time frame. What we want to do is extract what that chemist wrote down in that knowledge to bring that into a system. What we also need is a way to automate the experimentation on the back end, because we want to be able to understand and measure these properties so that we can look at the intersection of predictive models and how we might use a model to say, I want a molecule that has X, Y, and Z properties, because I think it would be valuable for this application space. We have existing data that has a lot of holes in it. It's biased data. It's data that's reported because it was the optimized solution. We want the unoptimized solutions. So we need tools on the front end to pull in existing data, and we need tools on the back end to automate and accelerate the process of chemistry, which is right now done by hands, just like these in a lab. How do we take analytical tools that can deal with high throughput information and actually automate and develop the experimental tools that can rapidly assess a property of interest? And how do both of these things feed into the representation? So instead of a molecular graph and a structure-based representation, how do I actually represent the dynamics and the physics of what's happening? And when does that matter? It doesn't matter in every case, but we don't understand when it matters. We don't understand how much data we need. We don't understand how much of the space we need to explore. So I'm really interested in bringing all of these pieces together to develop tools that are translatable and deliverable to users who care about developing the next new energetic or the next new simulant. But actually thinking about this from the context of how do we develop those tools and in the process understand the chemistry and the mapping of the molecule, not the structure, but the molecule, and what features of that molecule are important to the property, so that we can then use this tool set and this new fundamental understanding of chemistry to accelerate and move this process along so that we can, again, as you've heard so many times during this symposium, to make what we do better and faster. So I really look forward to your questions in terms of what I've set up today and the ideas and platforms that you have and you're working on that could come and help address this problem.
All right, thank you. Thank you, Anne. With that, I think we're going to start to address some of the questions asked by you, the audience. Let's start with one to Bill. To what degree do you expect computation and modeling to play a role in the materials development activities that you outlined?
Awesome. Thanks for the question, actually. So I was sitting here thinking, what did I forget? So definitely computation and modeling. I think we're seeing a lot of wonderful new tools that are available. These absolutely should be used. And I would also say that the tools that we have today are not complete. When you look at how the pieces that we have these exquisite tools that can go from quantum level phenomena all the way up to vehicle scales, and we've spent a lot of time trying to link those models and go the whole route. Use those, absolutely. In fact, I want to see the materials developments, even in silico, connected all the way to platform performance. And so that multi-scale model capability is really important. But actually, like Anne and Mike, I don't believe that those tool sets are complete by any means. They're purpose-built. They tend to have a very narrow sweet spot. And if you use them right for the right problem, you get good results, or at least indicative results. I go back to the old quote, and I forget who it's attributed to, but all models are wrong, but some are useful, and so use them. But I think also stretch your minds and think about what other modalities of modeling, like the ones that Anne just outlined, can help us go faster and integrate those in. So thanks. Yes.
Good. Okay. So the next question is for the it's for Anne. And it's kind of a general question. You talked about properties and you talked about data. So the question is, what properties are of most interest to DARPA? And what types of data are required?
It's a great question. So in terms of properties, again, I think about from the fundamental perspective, there are molecular properties that span application space. And so I think if we think about solubility and permeability and toxicity and reactivity, those types of things, having an experimental platform that can measure those things and then help us understand how that maps to an application so that I can develop, maybe I have a platform to develop medicines that I can measure those things on, but ultimately they can be used for an energetic where we've been looking for a solution for over 40 years to beat the standard energetic that we have now.
Good, excellent. All right, so Mike, I didn't want to give you an easy question.
Oh.
So we struggled for a hard question. So here's one that we thought you could tackle.
Is it to do with hops?
No, no, that comes later.
Okay.
The question is, what are the properties of classical fields that are similar to entanglement?
Okay, well, the entanglement is really just a mathematical statement of, say, 2 degrees of freedom no longer being separable in a mathematical model, but being the function is an irreducible function in terms of those 2 degrees of freedom or variables. So in terms of classical experiments, you can entangle spatial modes, amplitude, polarization, spin, temporal mode. You can entangle 2 or more of those, meaning that you can mix the fields in a way that you can't then separate mathematically the description of the field into a product of the 2. So if you think about a simple equation like A plus B convolved with C plus D, I can separate that into A convolved with C and so on. But if I have A convolved with B multiplied by C convolved with D, I can entangle those parameters. And there are experimental methods of creation of photons and wavefronts which naturally lead to that kind of entanglement. A simple example in the spatial domain. Am I going on too long answering this? So for example, if you think about diffraction from a slit or a square aperture, then the diffraction pattern I can write, if it's a perfect square or slit, as the product of the diffraction from a one-dimensional aperture in this direction and a one-dimensional aperture in this direction. And that product it's infinitely separable, no entanglement. But if I was to have a square aperture and make even a small indentation in one corner, you can show mathematically that the function you get for that diffraction pattern is irreducible. It doesn't factor at all. So it goes from infinitely separable, you can represent it as an infinite product, like a polynomial, to now a function that has just one term in it, and you cannot factor it. It's totally entangled. And we haven't really been thinking about classical optical systems in this way because our brains say that's classical optics, that's quantum optics. Is there a dividing line between the two? Well, people thought it was entanglement. Well, it's not. And maybe there is no dividing line between the two. And I think that's interesting to explore.
All right, so we're almost out of time. There's one last question which I think I would like to direct to all of you. Entanglement, is too easy. I want to ask something that's really challenging, and that is I want you to look into your crystal ball. Based on DSO's current and near-term investment portfolio, all I want you to do is to tell us about the big wins that we're going to be hearing about at DARPA's 75th anniversary that we're thinking about or working on now. That's all you have to do. And let's start with Bill.
Okay. So I want to cure retirement. Oh gosh, why would I want to do that? So from a materials perspective, so much of what we do is in the lab it's in people's heads. It's the landscape not only of what works but doesn't work, and all the intermediate impossibles that led us to the right answers. And when somebody retires, that all walks out the door. And so a lot of what you're hearing here, I think, is our attempt to codify that knowledge in some tangible way so that we can go and query it and understand it and allow ourselves to not have lost the lessons of the past. So I want the DARPA Oracle for materials that I can ask it and say, okay, am I going in the right direction? Has someone been here before? And to have that in a tangible way.
Mike?
I have maybe two answers.
No, you only get one.
Well, okay. So one would be, I'd like to be able to attend the 75th.
No, that was his answer. So you have
But no, there's more.
Okay.
I'd like to be able to meet someone who's traveled back in time from the 100th at the 75th. Is that possible?
It's a very good way to buy stocks, I understand. All right, Ann, go ahead.
So it's unfair. I've had a little more time to think about this. But so I have two programs. One is about city-scale detection of chemical, biological, nuclear, and radiological threats. And one is about a portable system to destroy chemical warfare agents. I think both these systems will be fielded in 15 years time. But my hope is that one of my colleagues actually develops something to make those technologies unnecessary and obsolete.
Very good. All right, with that, I think it's probably time to wrap up and thank our program managers.